It's Friday afternoon, and a customer reports their analytics dashboard is completely blank. An AI triage agent is assigned to investigate the root cause. The agent does exactly what it was designed to do. It checks the error logs. Nothing. Validates the feature flags, queries the CDN caches, verifies the billing status. Every tool call executes perfectly. But 4 minutes later, the status still reads running. The agent has cycled 90 times and burned $2,300 in inference costs. The actual problem? The user had simply turned on an ad blocker. Look at this diagram of the Agentic call stack. At the bottom layer, we have the individual tool calls. They are highly secure, protected by timeouts and exponential backoffs. But wrapped around them is the top layer, the iterative loop. Industry-standard retry logic perfectly defends that bottom layer, but those exact same frameworks provide zero structural governance for the loop sitting directly above it. Large language models are explicitly optimized to be helpful. Without a defined ceiling, the model will continuously observe its environment, fail to find the answer, and reason that it simply needs to keep searching. Developers often treat framework defaults as safety nets. In reality, a default loop without explicit exit conditions is a blank check against your cloud budget. Every electrical system has a circuit breaker. It cuts power not because the current is mathematically incorrect, but because physical systems require absolute structural boundaries. The exact same logic applies to software. An iterative cycle without engineered constraints is an unmitigated enterprise liability. You might wonder how a system where every individual action operates at 99% reliability can routinely fail in a production environment. This chart reveals the underlying mathematical reality. An agent running a 50-iteration loop with a 1% risk per step doesn't maintain its original 99% safety rating. It accumulates roughly a 39% chance of at least one unintended side effect. That compounding effect applies directly to your cloud bill. Unengineered multi-agent pipelines running open loops routinely consume up to 15 times more tokens than single-turn equivalents performing the exact same task. You cannot evaluate system safety by looking at single actions in isolation. The loop inherently multiplies the risk of every decision inside it. Take the foundational React loop, where an agent observes, thinks, acts, and repeats. The standard implementation trusts the model to decide on its own when the task is complete. The required engineering fix is strictly mechanical. Impose a hard ceiling on the number of iterative checks. After 3 tool calls return nominal infrastructure states, halt the execution and force an escalation. Another archetype is the reflection loop. Here, an agent generates an output, scores it, reflects on the feedback, and revises its own work to improve quality. This diagram maps the echo chamber failure mode. If the generator and the evaluator share the same model weights, they share the same blind spots. A security audit loops 3 times, grading itself higher each pass, converging confidently on an entirely flawed output. To fix this, mandate diversity. Use completely different model families for generation and evaluation to break the shared bias, and strictly cap the total number of reflective cycles. Left untreated, any self-assessed loop will naturally trend toward one of 2 outcomes: infinite execution or extreme confidence in the wrong answer. Many teams attempt to solve this with a human-in-the-loop architecture, dropping checkpoints at the beginning and the end of a long workflow, but they ignore the middle. An agent processing a mortgage application might pause for final approval at step 11. While waiting hours for a human to click yes, it has already pulled credit bureaus, ordered appraisals, incurred third-party fees, and triggered strict regulatory disclosure clocks. This timeline visualizes the exact correct placement of human checkpoints. A human gate must be inserted immediately prior to any sequence containing external costs or regulatory triggers. The rule is non-negotiable. Irreversible actions must be mathematically gated beforehand. They cannot be arbitrarily audited after the fact. Then there is the eval feedback loop. Unlike the runtime loops inside an agent, this is a system-level meta loop operating asynchronously between deployments. It defends against subtle quality degradation. If a customer service agent's tone slowly drifts from professional to overly casual over 3 weeks, no single response will trigger an error alert. You need continuous background evaluation loops sampling production traces daily. This is the only mechanism that catches statistical drift before it escalates into a public incident. Human intervention only protects the system if it is systematically engineered ahead of irreversible external actions or run entirely outside the critical execution path. The complexity multiplies in a multi-agent coordination loop, where the output of one agent serves directly as the input for another. This structure maps the cascade failure mode. An extractor agent sends flawed data to a validator. The validator rejects it. The extractor retries. Suddenly, a single misconfiguration exponentially duplicates into dozens of simultaneous retries across downstream systems. The architectural fix cannot live inside the individual agents. You must enforce strict limits on inter-agent round trips at the orchestrator level. This brings us to the first principle of loop engineering. Declare your constraints before the cycle ever begins. Every loop requires 3 mandatory exit conditions: confirmed goal completion, total budget exhaustion, and the detection of an irrecoverable state. Furthermore, the system must measure progress, not just task completion. If 3 consecutive iterations show a flat convergence score, the loop has lost direction and must halt before the budget burns out. You cannot rely on self-assessed exit conditions. Asking an AI if it feels satisfied with its output is not a constraint. Confirming a valid ID via an external system API is. We return to the circuit breaker. Engineering the agentic stack means building a rigid, unyielding container around the iterative process itself. Rigorous loop engineering systematically removes reliance on the model's helpfulness. It replaces large language model hope with verifiable, deterministic boundaries. By 2026, the landscape shifted. Major agentic frameworks now ship with looping enabled as the default execution model. The barrier to entry has vanished. The financial stakes are immediate. Agentic workloads are rapidly approaching 20% of all enterprise AI spend. When an unbounded loop runs rampant, the damage registers directly on your cloud infrastructure bill, multiplying operational costs in real time. The tooling to control this is now fully mature. Battle-tested open-source primitives like Temporal and AgentOps finally allow engineers to implement durable workflows and granular per-iteration state tracking. Because these primitives exist, there is no longer any valid engineering excuse for shipping unengineered loops to production. Teams that fail to adopt this discipline will spend the next 6 months discovering critical loop failure modes one by one in the worst possible environment, live, customer-facing deployments. Your action item is to run a strict loop audit on your most critical production agent tomorrow morning. Verify 3 absolute exit conditions. Confirm per-iteration traces are actively emitting. Ensure irreversible actions are strictly guarded. Relying solely on standard retry logic is hoping your system works. Loop engineering is the structural discipline required to guarantee it.